Hey folks, thank you for joining us for this session today on how to become a streaming data engineer. So my name is Tun Shui and I'm going to be the host for you today. I'm the VP of Data and I look after developer relations at Quix. So yeah, this one is an exciting one for me and I'm going to bring Thomas onto the stage shortly. But first of all, I'm going to give a few minutes for everyone to start entering the chat rooms. And in true tradition, if you've seen me do this before or you've spoken to me at events and conferences, the topic normally turns to that of ice cream. So as an icebreaker, could you please share what your favorite ice cream flavor is in the chat room? And we'll allow everyone to settle in and we'll start very shortly. I should add mine. Mine is pistachio ice cream. I spend a lot of time in Italy as well, so I travel every year. And there it's called pistachio gelato. So always have to get that part right. So yeah, please do share your favorite ice cream flavor. Whilst you're doing that, let's talk about why you're here. You're here because you love data. You want to be at the top of your game and you want to become a streaming data engineer. So I've spent a lot of time in my career being a streaming data engineer and a data engineer before that. And that helped me to really progress in my career. And the value that a lot of companies had was that it unlocked lots of new use cases. So today, Thomas is going to go through those and you're going to get to understand why a streaming data engineer is the most powerful of all data engineers. The agenda today is this. We're going to go through a lot of introductions. This is the first in a series that we're going to be doing, each one progressively and progressively adding to your knowledge and a continuation of the previous. So we're going to be sharing the full source code and the slides after this session too. So all you need to do is sit back, watch and enjoy. And on that, I'm going to introduce and bring to the stage Thomas, who is the CTO of Quix, and he's going to be taking you through the session today. So I'll hand it over to you. Thank you, Thomas.
Hello, thank you, Tun. Hello, everyone, and thank you for coming here today. So let me introduce myself and then show you what we're going to talk about today. So I'm Tomas Neubauer. I'm CTO and co-founder at Quix. I'm from Prague, Czech Republic, and I have spent my whole career working with sensor data, real-time sensor data. And as a result, I had to process them in various jobs and various use cases. And that's why I have founded with my co-founders Quix as well and built Quix Streams, a library with my team. Now, stream processing and this technology come to me as a kind of necessity in my previous job because we have been processing data from F1 cars. And it was quite challenging use case. We spent lots of time evaluating different technologies, and I'm going to talk about that a bit later. But basically, the amount of data we had to process was huge, and we had to also respond quite quickly to incoming data. So it's quite interesting use case for stream processing, and I will share a bit on the end about that. So can I just ask you quickly a question just to understand my audience? Who is, and can you please post it to your chat, who is using Pandas on a daily cadence? And who is using Kafka? And it could be professional or home project, doesn't matter, but just whoever use Kafka, publish messages, consume messages, doesn't matter really. Great. So let's start with the streaming data engineer and what this role is about. So it is basically a data engineer who is able to build real-time redistributed systems using technology like Kafka, Pulsar, Redpanda, together usually with Kubernetes or similar orchestration engines. So on top of the data engineering role, it's a set of skill sets that including these technologies. And we're going to talk about fundamentals of that in this today and more in the next episode of this series. So let's start with stream processing. What is stream processing about? What is the motivation to use it? because it's not a silver bullet for everything. And what are different approaches to solve stream processing? So this is a classical old-fashioned batch-oriented architecture. And imagine an application where you get data from your phone. That could be, for example, Uber, where a driver and passenger sending their GPS locations and trying to meet in the middle, somewhere on the street. Now, that would be data getting into some WebSocket gateway or any sort of cloud gateway where we get data from the phones. And in an old database-centric architecture, we would sync that data into database. And then we will analyze it with SageMaker, Google Colab, etc. And then build a batch job, which will be loading this data into job on a regular basis in some periods. It could be a minute, 5 minutes, an hour, and analyze the data, found patterns, do whatever you can imagine, and then publish the results into another database, which then the database would be queried by application. Now you can imagine that in the Uber case, that's not really possible. Why? Well, number one, we need more real-time feedback from our system than 5 minutes or minute or even 30 seconds if we get to really fast microbatching. We need instantaneous results. Second, now in this architecture, what is basically a bottleneck here is a database, because in this case, database has to handle ingestion side, but also a query side at the same time. So we're kind of stressing this technology to perform as our overall architecture scales. Now, the problem with that is databases traditionally struggle with the scale. And although they are cluster sharded databases these days, they always come with a cost, and there is a bottleneck ceiling to the scale of a database. So as a result, streaming technologies were invented, like Kafka in LinkedIn, which are able to scale to a huge amount of data. And so if we opt for streaming architecture here, what's going to change is that now from the gateway, we're not going to send data to database. We're going to send it to topic in a broker. That could be Apache Kafka, could be Pulsar, Red Panda, or any similar broker technology from different cloud providers. The difference is now that topic is scalable, fault tolerant, persisted in a lock, and gives us a lot of options. So we're going to sync this data into database because we want to analyze this data. We want to be able to understand patterns and what we're getting from our sources. So that's still the same. However, we don't need to do this from both sides. We don't need to stress this database to be queried very often. We just query it for analysis. But we sync the data without a need to be real time. And then we process this data in flight, in memory, with our processing service, which will subscribe to this topic, analyze the data real time, and publish it to another topic. Now, in this case, there's no delay. This is basically happening real time with roughly 10 milliseconds gap between these two topics, plus obviously whatever we compute in that service. It's a push mechanism rather than pull. And also, we don't need this database to be a part of production system anymore. So this system can work at scale without database, and we can decide what we want to persist. And then the results of the output topic of the service will be pushed to applications, to probably a WebSocket gateway as well. So when we need to build architecture like this, there are a couple of rules, a couple of conditions If one of them is met, then you should look if you are interested in adopting stream processing architecture. If more of them are met, even better. So number one is if the amount of data is huge. In that case, dumping data raw from your data source into database might be very costly and inefficient option. Because if you're working with, for example, sensor data or financial data, healthcare data, you might need a different specialized databases for your use case. And if you have time series database, you can't just simply dump a raw JSON from your data source in it. You will render it pretty much unusable. So as a result, you want to build some pipeline that will pre-process this data before you land them into database. And that could be filtering uninteresting data, normalizing data, which we will do today, joining data from different sources or different sensors, downsampling if you are not interested in a raw frequency of your sensors, but maybe some aggregation is enough. And all of that happens before you actually touch the database. And then the output of this pre-processing is then synced to the database in question. What you also get from this is a nice back pressure mechanism. So if your database can't keep up with real-time data, you can use Kafka lock to persist data at different speed than being ingested. Second condition is when you need to react to data fast. And that could be some sort of critical alerting. So when 5 minutes delay to finding about a critical situation in a nuclear reactor is too much, then you need to deploy a system like this. And then any sort of application like Uber or food delivery, when you need to connect different users and the interaction need to be real time. So realizing that your food was delivered 5 minutes ago is not enough. And third, last condition is when you really need fault tolerant architecture, which will make sure that whatever happens with your underlying hardware, you will not lose any data. Now, one or more condition met, stream processing is your option. So then there's a multiple different solutions in the market to build stream processing pipelines. Lots of them are in SQL. There's a lot of Java options. And today we're gonna talk about Python option, which is where you use Python to process your data. Now, that might be handy if you are interested in using any Python ecosystems available there. So any pip package like NumPy, SciPy, Pandas, scikit-learn. If you want to use machine learning or LLMs, if on any of those packages and libraries are close to your use case, it's a good idea to use Python. There's also certain aspect of Python that is easier to learn than, for example, Java, and it doesn't have the low ceiling of SQL. So with the SQL, you will quickly get to the boundary of what this language, or it's actually not even language, can express. And as a result, if your application is a bit more complicated than just simple analytics queries, then Python is also a better option. Cool. So with stream processing behind us, the most important technology to grasp is Kafka or similar broker technologies, because most of these concepts will apply to Pulsar and Red Panda, for example. So these fundamentals are important to understand how to build scalable, fault-tolerant resilient architectures. So first is Kafka topic. Kafka topic is the main thing in the topology of a broker technology. It's a feed name or category of your data. Good practice is that each topic has one data schema, but you will find out that that's not always the case, but it's a good practice. You can enforce that with schema registry as well. Now, topic could be subscribed to by multiple consumers and also multiple consumer groups, which I will explain in a second. And each topic maintain a log of data, which means that every record you publish to this topic will remain there for a specified amount of time, which is very useful when you have any sort of restart or hardware failure in your architecture. Now, each topic have different partitions. That is, you basically partition your topic into multiple subtopics, tiny topics that you distribute across the cluster. Each topic gets replicated, so you can send data twice, 3 times to make sure that if the broker node in a cluster where you're sending your data is down, streaming is ensured. And also, it's immutable. So once you send the record to topic, you can't change it. Now, every time you create a new topic, you're going to have to set certain configuration options, which I'm going to show you in programming session. Now, the second important concept in Kafka, and it is really important, and we will configure this straight from the start in our coding session, is Kafka partitions and consumer groups. So each topic is split into multiple partitions. These partitions are redistributed over the nodes in your cluster. And that means that your amount of data can increase, and you can just add more partitions and add more nodes into your Kafka. So you can horizontally scale until pretty much infinite amount of data. And then when you process your data, you will create what is called consumer group. So let's say that you create a new microservice that normalize your data. That's what we're going to do today. And one service can't keep up with ingestion rate of your data. Well, then what you're going to do, you're going to add more instances of the same service under one consumer group ID. And then what's going to happen, data will split evenly into these instances. So you can add more compute power horizontally into your processing. Now, the way how data assigned to different partition could be configured, but by default is by message key. We call them streams. So each stream is consisted from one message key, and you have a couple of guarantees of that concept. One is a message order. Each message in one stream will maintain the order in the system. So you can rely on that the message that comes later will never be consumed before. Secondly, you get stickiness of these streams into instances of your consumer group. So in this diagram, you can see a blue stream is always consumed by the first instance of this service. When that is changed for any reason, Kafka will handle that, and client code has a chance to react to this situation. And last, before we go to code, is checkpointing. It's also a very powerful concept, and we're gonna immediately use it for our benefit in development. So as data gets streamed into a topic, we will process it and checkpoint the offset of messages that we have already processed. In other words, we're letting Kafka know these messages in this topic are already processed, we took care of it, and it's gone. So when you get restarted for any reason, that could be you updating your code or you have hardware failure, you will start from the last checkpoint, from the last commit that you have done, which means you don't have to reprocess all the data in a topic, but it also means that if there were messages published by your source where you have been restarting or you just were down, you will not lose them. They will just get consumed when you get again online. Just note that there's different offset per different partition. Cool. So before actually I start talking about Quix Stream library, let me introduce you to an end result of our demo application that we're gonna build partially today. And in the next episode, we're gonna basically build different parts of this architecture until we get the end result. So I will go to Quix Cloud, where I have here a different project, where each project is represented one by one GitHub repository. And what I'm gonna show you today is a public GitHub repo, which you can fork and you can have a play with it. It's published under open source license. So here we have a crash detection project, and here I have environment, which is reference or binded to a main branch. And here is our pipeline that is roughly what I have showed you in the slides. So we have input gateway, some processing, which is converting the format to a different. We have a sync to Influx database, and we have a crash detection, which detects a crash of a device. So imagine that you have a phone on your handlebar and you're cycling, and when you crash, we will detect that. And then we have here a front-end service that consumes that data. So now I'm going to go to an application called Sensor Logger. I will show you that in a second, how to use it. It's an amazing free app in iPhone or or Android, but you can use to send various sensor data for your development. So I'm going to start sending data. And here, if you go here and I'm just gonna double check we are producing the right, yeah. Now you see it's sending a lots of data. Actually, it doesn't for some reason. Let me run the service again. There we are. So now we're sending data, and you can see it by the green bars in the topic. And if I go here, now you can see this front-end application, which taking the location of my phone. So I'm in a Prague, as you can see. It's also getting the altitude and battery level and speed, which is quite low because I'm stationary. And it's getting a GeForce data from my phone. Now, also, when it starts sending properly, it usually takes a moment to initialize. Then I will shake my phone to show you the real crash detection. There's some problem probably with the signal, but there we have it. So now you see I'm shaking my phone, and we have to get a detection of a crash, which in this case is a machine learning model that we have trained on historic data. And this is basically what the end result can look like. But today, we're going to do something much more simpler. And we're going to start with the left side of this pipeline. So I'm going to go and switch to a streaming workshop episode 1, which is a completely empty GitHub repository. I have it here, and there's nothing in it. And there's a branch called EP1, which I'm going to switch to. And I'm going to show you from the scratch how you can build this application by yourself. So first, we need a service to ingest the data into. So I'm going to go to code samples, and there's a Flask web gateway. Now, this is a template to build exactly that sort of ingest gateway service that will take the data from different forms and will send it to a topic. So we basically, in a nutshell, going to build a Kafka producer in our environment. So let's call this web gateway. Great. So this service is now here, and it just has 40 lines of code. Basically, we have one endpoint called data, which accepts HTTP post, and we don't do anything with data. We just straight publish that message into topic. And this is important, that we don't do anything with this data in a producer. Why? Because we can't leverage Kafka yet, because we haven't entered the realm of Kafka world, where we have data resiliency, fault tolerance, and scalability. And as a result, we're trying to mitigate any problems with our custom code that we could introduce here. So that is why we're keeping this service as simple as possible. So now I'm going to deploy it, and I'm going to use an output topic called raw data. It's a new topic, and I'm going to have 4 partitions, and I'm going to limit it to 50 megabytes of data. And maybe after 158 hours, we are no longer interested in the data. Great. And then I will give it a public access, because I want to be able to send data to this service from my phone. So I need this service to be publicly visible on the internet. Great. So now this service is being deployed into my environment. And here you see that I can use this public code. I will copy it. And now I will go to my phone and share my phone screen so you can see. So here I have sent myself actually I haven't yet. So I'm gonna copy this. Sorry, I'm gonna have to, for a moment, stop my share, send the messages for myself, and now I'm gonna re-enable my screen share. Cool. So now I should get that URL in my phone. I will copy it. So this is the app called Sensor Logger. And here, if you go to settings, you can see in data streaming, there is and I'm going to paste it there. And I'm going to append data. That's important because remember, we have a data endpoint. Cool. So now I'm going to press start and go back to our platform. And you can see that we're already getting data into the topic. So that's great. We can go and investigate this data. Amazing. And this is the data format we're getting from this application. We have some envelope with some metadata, and the actual payload, which contains sensor enabled in this app. Now, this is not really a format that is particularly helpful for any downstream processing with sensor data. It's also not really helpful to time series databases like Influx, which is probably the best choice here, considering we have a lot of time series data to persist. So we're going to have to build a service where we can manipulate this data to something better. So let's do that. So let's go to GitHub. And there's many different ways how you can develop this. You can do it locally. You can do it in our platform. Or you can, for example, use GitHub code spaces, which I'm going to do today. This will basically give you a browser-based Visual Studio Code with all the dependencies you can get. So you don't have to spend time in installing Docker or Java or Python or whatever you're doing. It's all available. Great. So if I close everything, what I'm going to do here is I'm going to use Quix CLI. Now, this is a command line tool which helps you to connect your code with your infrastructure in a Quix cloud. And it's very handy for development. So here, first I'm going to do Quix use, and I'm going to choose what project I want to build. So in our case, it's a streaming workshop, episode 1. And then I have here already a web gateway service, and I'm going to switch to a different branch. So now I think what's going to be maybe even better if I start this from scratch, because you can see it, how it looks like when you don't have the service running. So the episode 1 branch, and then let's start again. So the first thing I'm going to have to do is to go Quix CLI. And here I going to get a command to install it. Let's make it a bit bigger so you can see it. Great. So you can see we already have the web gateway service there. That's because we have created this service in our cloud interface. So now, first I would basically install our CLI. And then first thing I have to do is do a Quix login. That's because I need to authorize myself against my cloud user account. That's done. And now I can do Quix use. And I'm going to use the workshop and episode 1. Great. So now let's build this new microservice, which is going to pre-process this data before it can be sent to database. So I'm going to do Quix local apps create. It's going to give me an option of various templates, and I will choose the starter transformation because this is transforming data. I'm going to give it a name. So let's give it data normalization. Cool. So we have a folder here with the boilerplate code. So that's great. So let's go and install Python plugins. Let's go to the folder. So data normalization. And first thing we have to do is to create a Python virtual environment. So I'm going to do Python m vn. Now I will do it in the root of the project because I just want one environment per whole monorepository. But you can have one per service. It's just a bit more involved. Great. So now we have that done. I'm going to just activate it. And then I will install all the requirements of this new microservice in that folder, which means that this should now get colors. Nice. Cool. So we have this service ready, and we're going to do first a couple of changes, which are going to leverage checkpointing and offsets that we have discussed in the slides. So first, I'm going to import UID, and I'm going to change the consumer group, remember, to a dynamically generated one. Why I'm doing that? Because unlike in production, where I want to resume where I left it, here, I don't want to work with data that are changing constantly. I want to work with static data. And this is exactly what a combination of randomly generated consumer group and earliest offset reset will give me. And then I would comment out an output topic. Cool. So now this is ready. And before we start coding, let's just walk through a couple of concepts of this library. So if you would do this by yourself without Quix Streams library, you would have to subscribe to a topic and then repartition data into streams that you need. So they might not be partitioned as you want in your code. Imagine that you're getting data partitioned by a user, and you want to do aggregation based on location of a user. That would require what we call a group by, basically restreaming data using a different partitions. Then you have to deserialize your data from whatever that format is using, so JSON, protobuf, arrow, into tables. And then we have to abstract ourselves from a concept of messages, because at the end of the day, we care about data, not how they've been sent. And then if there is a stateful operation, which we're going to cover in the next episode, we have to take care of the state in memory, but also at rest, because at some intervals, we want to make sure that our state is not lost. We have to coordinate all of that with the checkpointing that we have already discussed. And then we have to publish the result to output topic. Now, that's quite an involved process, which I would not recommend anyone to just do for one use case. And so basically what we have done with the Quix Streams is take all of that and we package it under a pandas-like interface. What that means? Well, what we have found out is that streaming as a concept might get quite unintuitive when you're trying to do it low level. And as a result, there's a steep learning curve. And most people are used to work with the static data using pandas and transform them in Jupyter notebooks. So basically, this is an attempt to bring that muscle memory, if you like, into streaming. So similar operations are done in static and batch, equally as in streaming, with the same interface. So think of it as creating a new column, which inherit data from different columns, which we're going to do today. Is same in pandas, whether that's static data or in streaming. Now, that leads us to a very important concept to grasp today, which is what we call streaming data frames. Now, you can think of it as a virtual data frame that consists of rows that haven't arrived yet. You see, the data coming from the topic comes over the time as they're being generated. It is real time at the end. And so when we're working with the table, we don't have data yet, and that's the difference. But the interface is abstracting you from that reality. So although you might feel that you're developing and you're manipulating data, they will be manipulated when they arrived. So going back to our code, here we have a couple of sections of the code which I will walk you through quickly. First is loading environment variables into our code. Now that's important because we use them to connect this code to our infrastructure. And then an app object, which holds the lifecycle of this whole microservice. So it helps us to deploy this to container. It will gracefully shut down the code. And only thing we have to do is basically call a function called run. And then we just initiate a new instance of streaming data frame from input topic. So as a result, we can go to terminal and we can type Quix local vars export to get these environment variables that we need. So now you see that there's a new file with everything needed to run that, that code. We also need to tell it what topics we want to consume. So in our case, it's going to be raw data. And we want to output table data. Cool. And now the only thing we have to do is just Python and Python 3 main PI. Cool, we're getting data, but they are a bit hard to read, isn't it? So let's improve that. So we're gonna import another package called import JSON. And here on the line 17, when we're printing data into console, we're gonna dump it in a specific formatting. That will give us a bit more readable results. Now you see, I'm running it multiple times and always getting the same data. That's because what we have done at the beginning here. So now we can look into our messages. Amazing. Now, as we discussed before, not really helpful here to use this format. We can't really send it to influx or just process it. So because we have multiple rows in each message, and so let's do first a extraction of payload from each message. So basically, we're gonna take this payload and consider this as a row, this as a row, etc. That's quite easy. We're gonna use apply function. And we're gonna take a payload property. And because it's a one-to-n relationship, we're gonna use expand. And as a result, now we should get to output each sensor readout as an individual message, as you can see now. That's great. So now you can see each message independently. Now, obviously, these rows coming grouped in the messages, but we no longer care. Now, what we can also see that they are not really the same. Sometimes they have different information, like here is GPS, here is accelerometer. Now, that's not really practical. In the next episode, we will learn how to join this data together so we can confront one table from different sensors in our phone. But that's a stateful operation, which we can't do now. We have to enable stateful processing first. So today, we're just gonna filter them. So we're gonna say, I just want rows where we get and the name is equal to accelerometer. Now we should get all the rows that just contains one type of data. Great. And now what we're gonna do is convert this data into nicely tabular format. So we're gonna create a new function called transpose, where we're gonna get input this message. And first is we're gonna create the result row, which is gonna look like this. It's gonna have a time property, which is the same as the one here. And then basically we're gonna use the name of the sensor as a prefix of a column. So prefix is equal to row name. And then for each dimension of the sensor, what we're gonna do is we're gonna add a column to the new row, which is gonna be the prefix plus the dimension. So in this case, it's gonna be accelerometer dash x this number, okay? And that's it. And we're gonna return this and call another apply. Great. So now we should basically get a nice tabular structure in the result. I think I have misspelled this. This is values, if I'm not mistaken. Yeah, values. Great. So now we're getting a nice data in output, and we no longer need to actually print this as JSON because we got our streaming data frame finally. So let's get rid of this JSON here, and let's just get a nice tabular printout, shall we say. Now that's better. So we have first column timestamp and then 3 columns representing different dimensions of our accelerometer readout. So great. So this is almost what we wanted to achieve. Now, just to give you a bit of an example, what you can do now is let's calculate a new column, which would be a total amount of forces applied to this device. So I'm going to just create accelerometer dash total, which is going to be SDF X absolute value. And you can see that this is it's actually exactly the same as you would do this in Jupyter Notebook on the static data. But here, we're going to do it on streaming data. All right, so now let's print this, and I will make a bit more space. And just to be able to show you this, that it's working properly, I'm just going to change this from earliest to latest. Why? Because I'm not longer interested in static data. I'm actually want to show you real-time data coming from my phone, so we can see that it's actually working. So now, if I start streaming again, you see that I'm getting 3 columns, and if I now start shaking, the last column's going to high numbers. If I put it back on table, it's again 0. Up and down. If I make it a bit bigger, zeros all the time, and now numbers going up, down. Great. So now I'm in position to react to this data, build anomaly detection, or just sync it to database. But we're running out of time, so that has to happen next time. So the last thing which we just want to do is uncomment this line to output this data into output topic. So going back to here, let's summarize what we have learned today. So we have learned what is to be a streaming data engineer and what it means to build real-time architectures that are able to process real-time data in a redistributed systems which are fault tolerant and scalable using technologies like Apache Kafka. And we've talked about how to use these concepts to make a fault tolerant, scalable systems in the code. And we use Python. And although today we haven't really leveraged the Python ecosystem, we're gonna do in the future by using a machine learning and LLM libraries to enrich and process data coming from our sources. And we have done an operation, which was the calculating the total forces applied to the device, which was basically a static batch-like operation in a streaming context. So actually, every time you receive the sensor data from my phone, a new column was calculated. So this exact code is now available in this public GitHub repository. You can fork it, and you can basically use it to build exactly the same pipeline without a single line of code because it's in a main branch. You can use it to build something else as a basic template with this stream logger application. There's many more templates available on our website if you are interested in different use case. So feel free to check out our GitHub. Give us a star on our GitHub if you like the library, or you're gonna like it when you try it. And yeah, I'm really thank you for you to coming here today and learning this stream processing. And if you have any questions, just leave the question in our chat or possibly in our community Slack later. Thank you very
much. Thank you very much, Tomas. That was great. You know, Tomas is famous around here for his live coding. And, you know, the rest of us always talk about making sacrifices to demo gods. Thomas doesn't do any of that. You see him live debugging. Love it. So thank you very much. We've got time for a few questions. Going back to how to become a streaming data engineer, we had this question. So I'm going to pull it up here. So there's someone called Steve who asked about their career choices. They're a bachelor student. They're learning data science, but they're always interested in open to learning data engineering. And his question was, any thoughts on which I should select as a career, data scientist or streaming data engineer?
Well, it's a tough question. So data scientist job is more about focusing on data itself and analyzing it, and what insights you can deliver from that data. Streaming data engineer is more about building real architectures and applying your skill set to building applications, whether that's in the cloud or on premise, and making sure they will work in production. Also, making sure that the architecture and the code is fault tolerant, scalable, and resilient. So it's a slightly different career path. Having said that, these two roles will work together, and one of the roles of a streaming data engineer is to actually enable data scientists to be able to work on directly on data and be able to self-deploy code into stream processing systems, because it's very important that data scientists don't work in silos, isolated from the real data, are actually able to test their models and their code.
Yeah, that's a great answer. You're going to see a lot of generative AI and more kind of AI examples in future episodes, and just content in general from Quix. You'll see that those two worlds are really colliding. We have those fantastic things like ChatGPT and large language models because of the hard work of data scientists. But to get the value out of these, companies are going to need data engineers to prepare that data, and real-time data is going to be utilized a lot more in these models as well for the future. So that was a great question. We've got another one here. I'm going to show this one here. This was kind of whilst you're talking about partitioning, I believe. So we've got a fan of partitions here. And the question around partition keying being handled behind the scenes. So can you talk a bit more about how that works?
Yeah. So we're going to talk about partitioning in the next episode, because it's very essential and key for stateful processing, and it's one of the most important feature of the Quix Streams is group by for repartitioning your data. So whenever you aggregating data, you have to make sure that what you're aggregating is in one partition, because then what you would get if you don't do that is that, let's say that you do a sum of forces applied to my phone. Let's imagine I'm calculating that. If I would aggregate this data and my stream is not composing my phone, I would get some in different instances of my code, and they would render this value completely incorrect. So you have to always aggregate your data you have to stream your data in partition in a way that you are intending to consume this data and process it. That's why you might get one data streamed to different topics, partitioned in a different way, because you might have a different transformation services in your pipeline. Now, it's quite a complicated concept because it's all related to how consumers assign to partitions in type of consumer groups. And if I go to the slides again, I recommend to go into this slide, where basically each color of these data points is one stream. In other words, one partition. And then as a result, each instance of a microservice is then consumed with that partition being assigned to it. But again, this is a more of a concept that we need more time to it. So I will explain this next time on a group by example, where we can partition this data from what they are right now to different partitioning.
Fantastic, thank you. Yeah, so that was a good teaser into future episodes. We're going to go more into stateful processing again very soon. So yeah, that's all the time we have today. So I just wanted to say thank you to everyone who joined and stuck around for the end, and thank you to those who asked questions. I hope you got everything you need, but if not, come join us on Slack. So we've got the URL there and the QR code. Please come and say hello, ask any questions there. Thomas hangs out there every day, so please do that. So all that remains is I want to say thank you again to Thomas. Any last words, Thomas?
Well, I would just want to say that I'm super happy to see Javi in the audience. Hello, Javi. It's our colleague who unfortunately was a bit ill for some time, so I'm happy to see you back, Javi. And thank you, everybody, for coming here today. And please stay tuned. We're gonna get more of this content, and we're gonna dial into stateful processing, machine learning, LLMs, everything in the next episode.
Amazing. Okay, thanks everyone. See you next time. Peace out.